Hi Year 12, we're still working through Chapter 5 here, but we're now up to 5G and we'll be looking at differentiation of the logarithmic function. Now let's read through the first few notes and see if that helps us out with any of the work today. The importance of the exponential function e to the x in calculus extends into the logarithmic function. So we know that they're the inverse of each other, and we reminded ourselves last lesson about that. And there's a little proof below associated with the differentiation of the logarithm. It's not too difficult, and so it's reproduced down below. So basically it's going to show us how we find the differentiation of log of x, or ln of x, the natural log. Okay, so it says using the equivalent representation of x equals e to the y. Now we know that we can place this x equals e to the y into log format. Okay, so we did that last lesson a lot and reminded us about it. So we know that e to the x is equal to the y. So we know 1, 2, 3, and it's written here y equals log of x, but I like to write it as y equals log e of x, like that. So e to the y equals x, e to the y equals x. That's where it comes from. Okay, so I've written that down there, that x equals e to the y. Now, let us differentiate that. Differentiating both sides, we get 1 dx. So we've differentiated with respect to x, and that's equal to e dy. So we've differentiated this side with respect to x and this side with respect to y. We rearrange both sides, and this is what we haven't done a lot of, but dx and dy are actually individual parts that we can multiply by and divide by. So what we've done here is differentiated here, and then we've divided both sides by dy. So on this side I end up with dx dy, so I've divided this by dy. This dy is cancelled out and I've ended up with e to the y. So what I have now is dx dy equals e to the y. Now, when we differentiate, we normally are looking at dy dx, and what we have up here is y. So we do want a dy dx when we differentiate y being log of x. So what I can do is flip both of these upside down, or find the inverse of them, basically. So if dx dy is e to the y, if I invert the left, I get dy dx. If I invert this one, which currently is over 1, it becomes 1 over e to the y. Now, dy dx should have our right-hand side in terms of x, because we're differentiating y with respect to x, and we know that e to the y is equal to x. So dy dx is 1 over x, because I've replaced e to the y with x. So dy dx is equal to 1 over x. So we've started off with this, which is also the same as this. So we now know that when we differentiate y equals log of x, I get 1 over x. And that's our rule. It's a handy thing to know how to do that. And I will highlight our rule there. And I'd like you to work through this and see that you can understand that, and we may need to use that at some form. So when we differentiate log of base e of x, or our natural log, ln of x, we get 1 over x. As usual, there is a more general form that allows for the case where x is another function. So if this x here was bigger than x and we had some other function x, the formula works for most of the problems that we will encounter, and so we can say that the differentiation of log of some function f of x is equal to the derivative on the function. So that's how I remember it. You can think of it as f dash of x on f of x, but it's the derivative on the function, and we're finding the derivative of this part f of x and popping it over itself. Okay, so I've just jumped over to the HSC formula sheet, and what you will find is that we have that on our HSC formula sheet. So when y is ln of f of x, so when y is log of base e of f of x, our derivative is the derivative on the function. So we've got that given to us there. Not to be confused with this one here, which we will also have a look at soon. But the derivative on the function. Let's jump back in and see what else we need to do. Okay, so we're back onto our worksheet. Let's have a look at the examples below. Example 1, differentiate the following expression. So our first expression in part A says that y is equal to 5x squared minus log 7e of x. So we want to find y dash, or dy dx. So our first part here, we're going to differentiate separately to our second part. The first part we are used to doing. So we're not doing any fancy derivative on the function. We're going to multiply by our power and get 10x, take 1 off our power, so 10x minus. Now, that 7 is going to stay there in front of our log, and when we're differentiating our log of x, we look at what's in the brackets after it, and it's the derivative on the function. The derivative of x is 1, so we'd have times 1 on the top line, and our function is x. And that's our answer there, 10x minus 7 over x. Let's look at part B. We have y being equal to log e of x squared plus 1. So to find y dash, this is our function here. So when we differentiate a log of base e, it's our derivative of that function, which is 2x over our function, x squared plus 1. So that's quite easy to work that one out. Okay, part 2. We're going to use log laws to simplify each expression and then differentiate it. Now the first one there, 2a, I would not use any particular log laws to differentiate this one because it's quite a nice, neat function after our log. So what I would be doing is still doing my derivative on my function. My derivative is 14x and my function is 7x squared. The only thing you need to remember with questions like this is you still need to simplify wherever you can. So I'm not going to leave that as 14x over 7x squared. I'm going to simplify that. So 14 over 7 will give me 2 on that top line. I've got an x on the top line, 2 x's on the bottom, so it's going to become 2 over x. So that one's fairly straightforward. Part B, however, here, I would do this a little bit differently to this one on the left as part A. I do B a little bit different because it's saying in the question to use log laws, and that's what I would do for this one. Because if you have a look at this function, I can't really put the derivative on the function in that case because it's a little bit complicated. So thinking back to your log laws, what happens when we had log of something divided by something? We simplified that by popping a minus sign in there. So I could write that as log of 1 plus x minus log of 1 minus x. Now that's still y, and now what I can do is I can differentiate each part separately, and each has a function which I can easily write in the form the derivative on the function. So what I'm going to end up with on my first part is my derivative on my function, which is 1 over 1 plus x, minus the second part, the derivative, and just be careful with that because I just made a little mistake before. When I differentiate 1 minus x, I get minus 1, so that becomes a positive 1 over 1 minus x. So it's just going to be your negatives that will mess you up a little bit on those ones, and that's our solution for that one. Okay, so I've just jumped over into the OneNote, into the extra pages that I worked through. I wanted to have a look at a few extra questions in there. So if you hop into 5G integration of ln of x, there's a couple of questions here, which I'll do the first one. It's asking us to differentiate by the product rule. So I've got x to the 3 ln of x. So we just haven't done one like this before with logs, so I thought we'll have a go at it. So in this case, we're going to use the product rule, because as you can see, there's two separate functions involved. So we're going to let u be equal to x cubed and v be equal to ln of x. So u dash is 3x squared and v dash is the derivative on the function. So you're going to check your product rule from the HSC formula sheet. So our y dash is v du dx plus u dv dx. So we're going to get 3x squared ln of x plus x cubed times 1 over x, which will simplify down to 3x squared ln of x plus x squared. We could actually factorise an x squared out of that if we wanted to, and we'd end up with x squared 3 ln of x plus 1. Okay, similarly, we could have a look at b here, but we'd be using the quotient rule. Now, normally we wouldn't tell you to use the quotient rule, but because we're still learning with these, we've sort of been a little bit nice. So here's our function y, and it's made up of u, which is ln of 1 plus x. That's our top. And our bottom, which is v, is x. So u dash is going to be our derivative on our function, and v dash is going to be equal to 1. So you need to know your rule. So it's v du dx minus u dv dx all over v squared. So you need to go and check that off your HSC formula sheet and make sure that you're writing it down the correct way. So v du dx becomes x over 1 plus x minus u dv dx, which becomes ln of 1 plus x, but all of it is over v squared. So I need to neaten that up a little bit because I can't leave it like that. So I'm going to divide the x squared into each part above and see if that's going to simplify my question for me. So let's do that. So we're going to end up with y dash is equal to x over 1 plus x on x squared minus ln 1 plus x on x squared, which equals, on this side, these x's are going to cancel out. So we've got 1 on 1 plus x times x minus ln 1 plus x on x squared. Okay, that's one way I could have done it, but I don't want to leave it like that either. I'd like to pop this over a common denominator. So I'm going to go one step further, and my common denominator is going to be x squared 1 plus x. So let's multiply through. Now, to make our 1 plus x times x equal to our denominator there, we've got an extra x. So I need to times my top there by x. Minus this one here already has an x squared in it, so I need to multiply my top by 1 plus x. So I'm going to have a 1 plus x times ln of 1 plus x. Okay, here's another slightly different one. Here's my function y, and y is equal to log e of 3x minus 7 to the 5, and we want to find y dash. So before I can do that, I need to think, well, I have a 5 up there, and with my log laws, I can bring that 5 down to the front. So before we find y dash, let's neaten up our y. So we're going to get 5 log e of 3x minus 7, and now it's in a workable format, so I can find y dash, which is going to have 5 still there. My derivative of the top is 3. I'm over my function 3x minus 7, so I'm going to get 15 over 3x minus 7.